Is this a wife?
Yes.
Is this a wife that is a teacher?
Actually, yes, she's a math teacher. High school math teacher. She's teaching seniors.
Ooh. What school is she at?
Westie.
Nice.
Yeah.
So is her, she has a bachelor's in math and then?
No, actually, she's got a minor in geology. She's got a bachelor's in English literature. And then she passed the GRE for math and is teaching math now.
Interesting.
She's kind of a polymath. So it's,
Interesting. That is kind of funny.
don't ask her about physics though.
Yeah. Physics is not something that is intuitive for most people. All right, so we'll wrap up the last piece of 6-7 this morning, and then we'll jump into 7-3. And then that's what will be on the exam a week from today, the chapter 6 material and then the one section from 7-3. So on Tuesday, we'll spend the whole day reviewing. Let me remind you that if you come down below to the end of this chapter 6-7 stuff, the end of this unit, there are 3 prior exams with answer keys that you can start to go through. Those would be a really good idea. The exam that you'll have a week from today is not going to be dramatically different from any of them. So if you go through these 3 prior exams, look at the answer keys, ask questions on Tuesday, you'll be well prepared for the exam on Thursday next week. There's also in my math lab, there's a sample homework that is meant to be a review also for the exam, which is mostly what we're going to be doing when we do this review day on Tuesday. I'll go through all these types of examples, and these are coming directly from that my math lab sort of practice for the exam 1 thing. So you can look at that. Lots of different places where you can study. And any questions you have, of course, come on Tuesday. We'll go through them and figure them out. So let's go to our chapter 6. We're working on, we had one last question that we hadn't finished yet with the force on a window. So we've got a window in a pool, it's submerged, so there's water pressing against the window. And the question is, what's the cumulative force on that window? And the first thing we see is that the window is round, which means we need to write down the equation of a circle. And any questions on the equation of this circle? If this window has a half radius, is there any question on setting up the equation of that circle? So the center would be 0, 1/2. So we do the x minus h squared, y minus k squared equals r squared. Is that all looking super familiar? All right, and then because when we're thinking about the distance across this circle, this chord, that distance across is horizontal. Anytime we measure a horizontal distance, we're looking at a change in x values. So we would want to take the curves that are the boundaries of that horizontal element. We want to take those boundary curves and write them as x values. So we isolate x for each of those curves. So in other words, solve that equation for x. This right-hand curve here, so this curve right over here, the right edge of that is going to be x equals the positive square root of that. All that stuff in there. So the positive square root. If we simplified this a little bit, if we squared it out, you would get minus y squared. You would end up with minus 1y, but then you distribute and you get a plus y, and the quarters are going to cancel. So that would be the simplified equation for the right side. All right. And the left side would, of course, be the same thing except with a minus right in front of that square root. And then if we want w, if we want the length all the way across, w is going to be 2 times this. W will be 2. And you can think of it in 2 different ways. You can say, oh, this distance right here is, which that function is measuring, the full distance across is just twice that. Or you could say, let's take the right x value, which is positive, the left x value over here, which is negative. You'd have root minus minus root, which is also 2 times the root. So you can think of it in one of those, either of those two ways. Doesn't matter. So there is our W. When we look at force, our cumulative force here on the window, we've set a coordinate system so that the bottom of that circle is at the origin. So when we do our integration limits, we're looking physically where the window is. So there's pressure all along from 0 up to what would be our upper y value there? 1. Because the window is half a unit in radius, so it's 1 unit in diameter, going all the way across from 0 to 1. The 4 will come into play in the distance below the surface, the depth. So then we're going to do our ADD. Let me write the generic up here. So we're going to do integral of ADD area. Integral of ADD area will give us force. And recall that when we talk about area there, that area means the area of that little strip, not the area of the window, just the area of a little strip. So A, acceleration due to gravity, 9.8. Acceleration, density, depth. The density of the water pushing against the window is 1,000. And then the depth of this element is, for the element, 4 minus y. So the depth at the bottom is 4, but the depth of that one element, that distance right there, this is 4 minus y. So that is how deep that is, because when we're doing that Riemann something, we're thinking of all these little strips stacked up. So we're finding the force along each little strip. And so at that strip right there, that depth is 4 minus y. And these things multiplied together, the ADD, that's the pressure at y. That's the pressure at that depth. So there's ADD, that's pressure. And now area. Area means, so that's going to be the width of the strip multiplied by dy. This is going to be the area. Right, that's the area that we're talking about. The area of a little thin rectangle on its side, a sleeping rectangle. So we found the width already, right there. So that's 2 times the square root, negative y squared minus or plus y times dy. So that red stuff is all the area of the strip. And now if we were to go through and carefully look at the units of all these factors in here, including the dy, all those units would give us units of force, units of newtons. And then the integration symbol sums them all up. So we will have, if we pull our constants out, we're going to have 9,800. We're going to have a 2. And then it looks like everything else inside has a variable in it, so it stays. So we have 4 minus y. And then the square root of negative y squared plus y times dy. All right. Now, if we have any hope of integrating this kind of directly, the technique we have to use is substitution. But we know that substitution is only going to work if whatever we let u equal, it would have a derivative outside of the root that matches it or closely matches it. More precisely, is a constant multiple of it. Let's just check real quick. If we were to let u equal negative y squared plus y, the derivative here would be negative 2y plus 1 times dy. And so the question would be, does that match what's on the outside? And the answer is no. No matter what we multiply this by, this negative 2y plus 1, If we wanted to match like the negative y, we'd have to get to negative y, so we'd have to divide both sides by -2. And if we divided both sides by -2, we'd have that. Oh, I divide by +2 because we need the sign to match. So let's take that away.
You're in the racer.
So if we divide out the 2 right here, we leave the minus. So if we just divide out the 2, we would have that. And that does not match. The y matches, but we have a negative. The negative matches with the y, but we have a +4 and a +1/2. So it doesn't match. So that means we cannot use substitution in the way that we saw on Tuesday. Okay, so what we're going to do is this. We have to be a little more clever with this one. So what we're going to do is break that apart into 2 integrals. All right? And what we're going to do is rewrite this 4 so that we do get some matching. We can always take a constant and rewrite it as a sum of 2 numbers, right? We need the 1/2 in order to get this chunk of -y plus 1/2. So what I'm going to do is rewrite this as follows. So we could multiply this out too, 0, 0, 16, 19, we could do that. And then we're going to have big brackets because we're going to have 2 integrals here, 0 to 1, although let me write it this way first and then we'll distribute it. So if I want a 1/2 here, I'm going to write 4 as 3.5 plus 1/2. 3.5 is 7/2. So I'm going to write this as 7/2 plus 1/2 minus y multiplied by this square root. All right, we can do that. And now we are going to think of distributing that square root to 2 parts. We're going to think of each of these as terms, and this square root is going to distribute to this term, and it's going to distribute to that term. Right, we can always distribute. We're allowed to distribute. So let's go ahead and do that. So let's come all the way over here. So we're going to have 19,600 all the way out in front. And then we're going to have a big bracket. And we're going to have 7/2 multiplied by the integral of -y squared plus y square rooted dy, 0 to 1. So that's the first part. And then we're going to have the second part, which is where we're going to have a nice, it's not a coefficient, but it's going to act kind of like a coefficient function that will allow us to do substitution. So we're going to have this factor out in front and then the square root. All right, so we have that. Let's focus on the right-hand part first, the right-hand integral, because we've already set up the substitution that we need for this right-hand part. Right, there's the substitution. We're going to let u equal the inside of the root. We take the derivative, we divide it out the 2, and oh, that matches exactly out in front. So substitution is going to work perfectly for that integral. So let's see what happens with that, and then we'll deal with the other one in a moment. So we're going to have this 19,600. We're just going to leave this integral alone for the time being. We'll get back to it in a moment. And obviously that cannot be solved with substitution because the derivative of the inside is not present out in front. So we'll have to use another technique, and the technique we did do last week, which was a geometric technique. We looked at, well, what does the integral of that function represent? And we'll see that it represents the area of part of a circle. So we'll do that one geometrically because it's not going to be able to be done with substitution. All right, so now we are going to have over here, we have plus the integral. We're doing substitution now. So let's see. This is going to be the square root of u. We said u is this inside, so that's square root of u. and then minus y plus a half times dy, that's du over 2. And the over 2, we're more than welcome to move to the front. So there's, and the limits of integration, of course, have to change. So let's get rid of those. We're going to take those away. Doesn't seem like it remembered my settings from Tuesday. Looks like I might have to change those. So the u's, when we plug in, when we come up here to the substitution step, when we plug in 0, what do we get? 0. And what do we get when we plug in 1? 0. Anyone can integrate from 0 to 0. What do you get? 0. There's no area beneath a point. So we can take that away. This is going to be equal to 0. That whole integral is equal to 0. All right, so now everything boils down to this creepy looking thing. So let's see what that means. So let's try to analyze that. Oh, and I multiplied out the 2. Now I've got to divide the 2. So that is back to 9,800 times 7. And then we have this integral here. So everything boils down to this. All right. So now we did already graph a circle, blah, 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 but let's just approach it from scratch. We're trying to integrate that thing. Let's try to understand what the geometric representation of that integral is. We know integration is an area under a curve. That's what it's finding. All right, well that function, the function that we're integrating is this. And we know what that function is. That function, right, all we did was simplify up here earlier. That function came from right here. Where was it originally? Right there, right? That's what it came from. That's the function under the curve. We simplified it by combining the things. But this is, and maybe I'll rewrite it again there. So 1/4, come on. 1/4 minus 1/4 minus y minus 1/2 quantity squared. So that's what that function is. And we know what the graph of this looks like. The graph of that is a circle. So this is a circle centered at 0. This is going to be centered at 0, 1/2. So we're just rebuilding the window essentially, right? And that function represents the right half of this circle. So this is that function right there. And if we integrate that function from 0 to 1, so we're going to integrate that curve from 0 to 1, we're finding the area beneath the curve, but because we have our function turned sideways, beneath the curve means between the curve and the y-axis instead of between the curve and the x-axis. Okay, we know what that is. That's the area of a semicircle. Right? We're just trying to find the area of that semicircle, and the radius is 1. So this is going to be pi r squared, r is 1/2, but then it's a semicircle, so we divide by 2. It's not a full circle. So it's pi r squared divided by 2. And this will give us pi divided by 8. So that's what that integral represents. It's the area beneath the curve on the interval 0 to 1. Well, the curve happens to be the right side of a circle of radius 1/2. So we find the area of a circle of 1/2, divide it by 2, we get the area of the semicircle. So that's going to give us 9,800 times 7 times pi over 8. So there is our answer, however many times 8 goes into there. Somebody multiply that 9,800 times 7/8. It'll go in evenly.
8,575.
Once again?
8,575 pi.
Thank you. And these are newtons, not Newton meters. We're finding force, not work. So that would be our force. So any piece of that, any part of that you're not 100% sure on. So there are times
Part
where,
that's zeroed out.
say that again,
Part
the part that's zeroed out? Mhm.
Yeah, can you explain what that's representing in the whole scheme?
It's representing nothing. It's representing zero,
I guess it's fair.
right? It's not, so the geometry up here, this is the geometry of this is finding the cumulative force across the window, but we can't do an integration directly, so we broke it apart into two integrals, and one of those integrals just happens to turn into a zero. So it's kind of just, so that piece of it's not representing any part of the answer anymore.
So basically, that top equation is equal to the left half of the bottom equation. Those are equivalent statements.
Say that once again, the top equation
So
being,
that whole thing there,
yep,
that equation is equivalent to the left half of the bottom one after you cancel out the zero. It's like the values of the two equations is identical. basically.
yes,
Yeah.
yes.
So you're basically adding a whole bunch of nothing that makes the equation more complicated.
Yeah, exactly. It's like, it's kind of like when you complete the square and you just put in that middle term, yeah, and then you're able to factor it. But when you put in that middle term, you need to add it and subtract it, so you're really adding zero. It's kind of like that, where you can have zero not look like zero. If you add and subtract the same amount, you've just added zero. It's kind of like that, where we just, when we break it. Now, if we broke this apart in lots of different ways, one of the integrals would not be zero. Like we took and we broke apart this 4. If we broke apart that and made it 2 plus 2 minus y and then distributed, then we'd have two integrals that were not, one of them would not be 0. But it just so happens that the way we broke it apart, we ended up with one that was 0.
And if for whatever reason we weren't integrating from 0 to 1, it also still wouldn't have been 0 for that second half. It just happened to.
Probably not. Probably not. Yeah.
With the boundaries we.
Because this function would have to be 0, it would have to have the same value for both endpoints. So this function just happens to be 0 for each of those x values or y values.
Just a lot of big old coincidences.
A lot of coincidences. There are no coincidences. All right, anything else on that one you want to ask about? So those are going to be the hardest ones whenever you have a circle, because the equation of a right half and left half deals with a square root, and anytime we have a square root, we kind of get stressed out. All right, let's take a look. Well, first off, does anyone have a random question from 6-7 or homework question from 6-7 or even anything in 6 before we go to chapter 7 while we're still thinking about these ideas? If not, we'll go to 6-7. 6-7. Chapter 7.
7-3.
7-3. The only section in chapter 7 we're going to cover. It's the only one.
Oh, hyperbolic.
So the hyperbolic functions are a group of functions that parallel the circular functions. So the 6 trigonometric functions that you know are more precisely the circular functions. They come from a circle. When we talk about trig functions, we have the circulars and the hyperbolics. Those are 2 different groups within trig. And so what we're going to do is look at how the hyperbolic functions are developed and how we find derivatives and integrals. There's going to be a lot more in the section, but we're focusing on derivatives and integrals. That's going to be our primary focus. We're not going to do a ton with hyperbolics. So the first thing is that the way the hyperbolics are developed is parallel to how the circulars are developed. The circulars are developed with a unit circle. The hyperbolics are developed with the right-hand side of the unit hyperbola. The unit hyperbola, x squared minus y squared is 1. Just like the unit circle, x squared plus y squared is 1. So they're developed with a hyperbola instead of a circle. Now, when we are dealing with, one of the connections has to do with this area here. This area that's formed up here with the unit circle. Do you remember what the formula for an area of a sector is? So if we have a sector of a circle, the area is?
Isn't it length radius? No, that's feet.
So there's the ratio that the formula that the three variables represent, but the area of a sector, 1/2 theta r squared. Area sector of a circle,
Yeah. Good job.
1/2 theta r squared. That's the area of a sector.
If theta isn't radians.
Theta is in radians, absolutely. All of our stuff in calculus assumes theta is in radians almost always. Like all those derivative formulas, theta's got to be in radians. Otherwise, you'd have to use a chain rule for derivatives. Okay, now, isn't this a unit circle? If it's a unit circle, r is just 1. So the area of this circular sector is really 1/2 theta. And if you multiply both sides by 2, you could say, oh, the angle is really just twice the area of the sector. You could say that. We've never done that in trig. You never solve for theta in terms of the area, but you could. And so that angle theta, or angle t, whatever you call the angle, matches. So twice the area of the sector, that's what theta's, that's what the angle is. And that is the connection, which again, you're not going to ever really talk about that in any detail, most likely. But it's the same concept down here. The hyperbolic angle, which is right here, that hyperbolic angle is going to be twice the area of that hyperbolic sector. So that's how the circulars and the hyperbolics match. It just so happens that the area there and the area there have the same general formula. Twice the area of the sector to get the angle. Now, the angle in a circular function is way more important. It has all sorts of physical representations. You know, we can see it right there, and it's really nice on a unit circle because this angle and this arc are the same in magnitude. All right, do you remember the formula for if you look at the radius of a circle and you look at the arc length, we'll call it s, little s, and then t. What is the relationship between those three variables?
S is theta r.
So s is
divided by r. Yeah.
what you said is right. R theta.
R
Yeah.
theta.
S is equal to r theta.
Okay. That sounds good.
And although this has a t in it, so let's put a t in it instead. All right, so that is the relationship. Some people, when you're in basic trig, sometimes one way to remember it is to think of the angle. I'm going to move this r and put it down here for a second. You can think of this almost like slope. Slope is rise over run. If you wanted to, you could kind of think of t as circular rise over run. The circular rise would be s, right? We're going up along the circle. That distance is s, so it's like rise. And then the run is just the radius. And if you solve for s right there, you would get r times t. Okay, and so if it's a unit circle, the angle and the arc are the same. And so that's one of the primary things that sort of comes out of a trig class is that, oh, the angle and the arc are the same. They have different units, right? If you're measuring the number along the arc, it's units of length. And if you're measuring the angle, it's the number of radians, but the magnitudes are the same. And that may feel weird to you, but you see it all the time. What is the area, let's say, of that rectangle? 1. What if I make this three-dimensional? What is the volume of that cube? 1. So it happens all the time where you can have magnitudes of magnitudes that are representing completely different things, area versus volume, or angle versus arc length. Right? So you can have magnitudes that are equal even if the units don't match. So certainly the units don't match on that area and volume thing. So it's the same idea. Okay, so unit circle, we've done a ton with that. That generates all the trig functions. This is going to be our unit hyperbola, the right side of the unit hyperbola. And the units right here, the coordinates right here, are going to be hyperbolic cosine, comma, hyperbolic sine. Just like on the circle, cosine and sine. So same idea. Now, up here, we have a lot of symmetry with the circle, so you're able to find those trig functions as they rotate around the circle. Here, there's nothing like the symmetry that you have on a circle, so that's part of why these are less important. That symmetry has a big role in all sorts of engineering applications. The one thing that is super important about these hyperbolics, we'll see in a minute when we look at these graphs, but you can see as this hyperbolic angle starts rotating, there's different pronunciations of this. I call them cosh and cinch. Some people will call them cosh and cinch. Some people will call them other things. They're not used enough to have sort of come up with a common name, but cosh and cinch, cosh or cosh and cinch. Most people use cinch. But when we look at the graphs, we'll start to see an important thing. We'll get to them in a minute. So when you think about sine and cosine, or any trig function, in a trig class, or in Calc 1 even, and then you think about the exponential function, there has never been any connection drawn that you've been aware of, I would guess. Like when you think of sine and cosine, those are in a different bucket than the exponential function, right? Maybe some of you have done some YouTube stuff and seen that actually there is a connection, but most of you probably would never guess that there's a connection between sine and cosine and e to the x. Like they seem completely different. So let's look at these hyperbolics first. And we'll talk about the connection shortly. So first off, the hyperbolics are defined as exponential functions. More precisely, the cosh is the average of exponential growth and decay. Right? E to the x represents exponential growth. E to the negative x represents exponential decay. And then we average them. So the cosh is the average of growth and decay, exponential growth and decay. Sinh is the average of the difference of growth and decay. E to the x is growth, e to the minus x is decay. If we subtract the two and take a division and divide by 2, we've averaged growth and decay. So we've taken an average in this one of the difference of growth and decay. All right. The other 4 functions totally parallel what we did with circulars. Instead of tangent, we now have hyperbolic tangent, which we usually call tanh. So tanh, the hyperbolic tangent, same ratio that you would have if it was tangent. Instead of sine over cosine, sinh over cosh. But same setup. Hyperbolic cotangent. Instead of sinh over cosh over sinh. It's the reciprocal. Just like cotangent is the reciprocal of tangent, usually we call this cotang. So tanh and cotang. Sometimes people will say sinh and cosinh. Sometimes. Normally we just call it cosh though. And then we get down to the 2 super weird ones. Sech, reciprocal of cosh, just like secant, reciprocal of cosine. Sech, reciprocal of cosh, and cosech. So tanh and cotang, sech and cosech, cosech reciprocal of sinh, just like cosecant is a reciprocal of sine. So it's a mouthful, for sure. We have identities that parallel the circular identities. Our primary Pythagorean-ish identities, we have cosh squared minus sinh squared is 1. So instead of sine squared plus cosine squared is 1, cos squared minus sin squared is 1. Once we look at the graphs, it'll be very obvious which one comes to the left of the minus in order to get a positive 1 on the right. And then the other two Pythagorean-ish identities you find in the same way that you would find the Pythagorean identities for the circular functions. If you divide through by cos squared divided by cos squared is 1. Sinh squared divided by cos squared is tan squared. 1 divided by cos squared is sec squared. So you do the same type of thing to get your alternate forms. Divide. Same thing you did with sine squared plus cosine squared is 1. Similarly here, if you divide this yellow equation by sinh squared, cos over sinh is cotan, so you'd get cotan squared. Sinh squared divided by sinh squared is 1. 1 divided by sinh squared is cosec squared. So, same idea. The one that we are really going to focus on this one. These two, I'm not going to ask you much about. If you're doing homework, yeah, you could look these up. This is probably the only one of those three you need to memorize. Would be that one. And then we have the odd-even properties. Same as with the trig functions. So this tells us that cos is even or odd. If you plug in negative x or x and you get the same y value, that means the function's graph is even or odd.
Odd. Or even.
Even.
Yeah.
So it's like squared.
So think of it this way. If you have your y-axis, the idea of an even function is that if you go over to x or over to minus x, the y values are the same. So when you look at that, what you should be visualizing is y-axis, go to x, go to minus x, and this says the y value at negative x and the y value at x are the same. So regardless if you go right or left, the y values are the same, which make it symmetric about the y-axis, which makes it even. All right. So this one is even, symmetric about the y-axis, just like cosine. Cosine is symmetric about the y-axis, so we call it even. Sinh. This says if you go to negative x or you go to x, so go to x, go to negative x, one goes up and one goes down. The y value at negative x, this is positive. The y value at positive x is negative. So if the y values are opposite in sign, that makes it odd. So that one is odd. And then similar to that, we have the tangent odds. So just like sine, cosine, and tangent. Same idea. Sine and tangent are odd, just like sinh and tangent. The sum and difference identities, parallel. We're not going to talk about those. We're not going to need those. We have double angles that you're going to maybe see this one. And that one doesn't even change from the circular function one. Sine of 2x is 2 sine cosine. Right, that parallels exactly. So you know that sine of 2x is 2 sine x cosine x. So that parallels exactly. The cosh one's the cosh of 2x is a little different in with regular trig functions. Cosine of 2x is cosine squared minus sine squared.
So just like how the Pythagorean switches signs.
Yeah, that one will switch signs. Okay, so let's see. And then we have power reduction. Here are the parallel power reduction ones. So you may need to use those for integrating a cosh squared or a sinh squared. Again, I'm not going to ask you to memorize those formulas though, but you should be able to look them up here. The only one you really need to memorize is that one. Okay, so that's how this world of hyperbolics is living parallel to the world of circular functions. And again, really the most important thing about hyperbolics, other than the basic derivatives and integrals that we're going to look at, is this graph. So this one up here, hyperbolic cosine, looks like that. The hyperbolic cosine is, and so that's the average. You can see the dashed curves. Here's exponential growth, here's exponential decay, and cosh is the average. And the important thing is that this curve has day-to-day meaning, and that curve is the solution to a really famous problem that was posed way back in the day. What is the mathematical equation of a hanging cable? You've got a telephone line. What's the equation of that? It is not a parabola. It is not, it's not anything other than that. And that took a while for them to figure out that the mathematical equation of a hanging cable, it's hanging under its own weight, is the hyperbolic cosine. That is the mathematical function. It's not, you cannot build it with any sort of polynomial. Any polynomial you try to match to a hanging cable will not match. The only function that will match is the average of exponential growth and decay. That will give you the hanging cable. And the hyperbolic sine is going to look a lot like a cubic, a lot like tangent, but it has no asymptotes. It goes out, it has no vertical asymptotes. The hyperbolic sine and the hyperbolic cosine do asymptotically approach each other. They approach this function right here. Don't need to know that. So now, if somebody says, is it cosh squared minus sinh squared that's 1? Or sinh squared minus cosh squared that's 1? When you look at those graphs, if you are going to combine cosh squared and sinh squared and get a 1, it becomes pretty obvious that you have to take the upper curve, square it, and then subtract off the lower curve, square it. If you want to get a positive 1, you have to do the upper one minus the lower one to get a positive. So that's, if you have in your mind the hyperbolic cosines hanging there, sinh is below it, cosh is going to come first in that Pythagorean identity. Cosh squared minus sinh squared is 1. So with the graphs in mind, you can remember which one comes first. And you can see graphically that the cosh is even, symmetric about the y-axis, and the sinh is odd. Sinh is odd. Okay, so let's take a look at derivatives. The first two are, of course, the foundation derivatives for the other 4, just like you did in Calc 1. Once you know those two, you can calculate the other 4 with the quotient rule. Quotient rule, of course, works. So those are the two we have to know for sure right out of the gate. Pretty easy to memorize. They are almost like the trig ones, the regular trig ones, except there's no minus sign. You don't have to remember that the derivative of cosine is negative sine. The derivative of sinh is cosh, the derivative of cosh is sinh. They're each other's derivatives, so that's a little easier in some ways.
Does that have to do with its relationship to E?
Yes, yeah, if you wanted to differentiate these, you could convert it over to the e's and take the derivative of the exponentials and get to it, for sure. You can also look at, if we look at those graphs again, the derivative of cosh here is clearly negative, slope of the tangent's negative, and sinh is negative there. Here, the derivative is positive, and cosh and sinh is positive there. So you can kind of see that they match. If you think about the derivatives, the signs all line up perfectly. But you can absolutely, we won't do it much. A couple homework questions might convert over to the exponentials, but it's interesting, but we're not going to do a lot with that. Okay, so how do we get derivative of tangent, or tanh? So if we want derivative of tanh, well, we're going to first write it as a quotient. So we're going to write it as sinh over cosh. And then use quotient rule. So we do low d high. So low d high. Well, they are each other's derivatives. So low d high is cosh, minus high d low. So, and that's all divided by low squared, cosh squared. So in the numerator we have cosh squared
Which is just one.
minus sinh squared, which is just 1, divided by cosh squared. So that's 1 over cosh squared, and 1 over cosh squared is sec squared. So same process that you used in Calc 1 to determine the derivatives of the, first you did all that epsilon delta stuff to figure out the derivative of sine and cosine, and then once you had those, you could use the quotient rule and all the other rules. So that's how we get to sec squared. So now when we look at our primary 3, by primary 3 I would refer to these as the primary 3, just like sine, cosine, and tangent are the primary 3 for the circulars. Sinh, cosh, and tanh, primary 3 for the hyperbolics. Bless you. And all those have positive derivatives. So that's what I think in my mind. Sinh, cosh, and tanh, they all have positive derivatives. And then the other ones, the other 3, they all have negative derivatives. And the negative derivatives all match what we already know. Like we know the derivative of cotangent. Derivative of cotangent is minus cosecant squared. So this is going to have a cosec squared instead of a cosecant, cosec, but it's going to be negative. Derivative of secant. Derivative of secant. What is derivative of secant? Secant tangent. So it's going to have a sec tangent instead of a secant tangent, but it's going to be negative because it's one of the alternate 3, not the primary 3. And then derivative of cosecant minus cosecant cotangent. So we're going to have a cosec cotangent, and it's going to stay minus. So the only sign that really might be something you have to think twice about is those two. But that should be, if you remember that the primary 3 are all positive and the secondary 3 are all negative, should be okay. But you can always calculate them from scratch from these two. Should take seconds. Okay, let's take a look at, we are not going to go anywhere near these two creepy looking things. Those are a little too off the beaten path for us. We're just looking at the basics. Tanh and cotang, integrals. Well, let's take a look at the first one. So the integral of tanh. First, we're going to rewrite it. Let's rewrite it as sinh and coshes, because we know sinh and coshes already. So tanh, sinh over cosh. And what form is that in? So we had a special form that was kind of a shortcut form, that not RCR, but we had another short form that we haven't looked at a ton, but a little bit. Log form. Log form. Because that denominator has a derivative that's identical to the numerator. The derivative of cosh is sinh. So this is in log form. So what we saw the first week of the class is that when you have something like this, you could use substitution. It would work if you let u equal cosh. But you can cut to the chase. If the denominator's derivative is the numerator, you automatically can just cut to the chase. The answer will be natural log of the denominator in absolute value. Now, we already talked about the cosh's graph. Isn't the cosh always positive? Cosh is the hanging cable. It's always positive, so you don't need the absolute value. So there is how we get to the antiderivative for tanh. How about cotang? So again, we're going to write it as a quotient.
Just the same thing.
Right, same thing. Right, it's in log form. The derivative of sinh is tanh. I said that wrong. The derivative of sinh is cosh. So the denominator's derivative is the numerator. So this is going to be natural log absolute sinh plus c. Sinh can be negative, so we can't get rid of the absolute values there. We need to keep them. But same idea though, log form, natural log of the denominator. That is how we'll figure out those ones. And again, we will not look at the integrals of sech and cosech. Those are very difficult, not worth our time. This is what we want to spend more time doing. So you all try number 20. Try to show that the derivative of sech is minus sech tanh. So use your quotient expressions, rewrite sech as a quotient including sinh or cosh, and then use the quotient rule. And let's see if you can get to that derivative. Anyone know another word for the hyperbolic cosine? There's another word that the Brits especially use for it. Begins with a C. Catenary? Catenary? Or as the Brits would call it, a catenary.
Yeah, remember that from art class, it didn't connect with the structure.
There's some connection to like a sleeping cat being in the laziest position, chain being, there's something about a cat.
I just remember catenaries and hanging chains.
Say again?
Just remember catenaries and hanging chains.
Yeah, yeah. Catenary. So you should be setting this up as 1 divided by cosh prime. So we're trying to find the derivative of sech. We'll rewrite sech as 1 divided by cosh. And then we go quotient rule. We already know our quotient rule. So we're going to do low d high. So low is cosh. What's the derivative of high? 0. The derivative of the numerator, or high, or that constant, that's going to be derivative of 1, which is 0. Low d high. Minus high. And then d low, sinh. Derivative of cosh is sinh. So low d high minus high d low divided by low squared. So we end up with minus sinh divided by cosh squared. I'm just going to separate that cosh squared into cosh times cosh. And so our final answer certainly is negative. And then we can just sort of pair this off. We can say, okay, well, we are going to think of cinch over cosh, that's going to be tanch, and 1 over cosh is sech. So that's going to give us our negative sech tanch. Everyone okay with that?
Can you go over that again?
So it's also possible, you can think of this as -1 times sinh, and you can think of just pairing off that fraction and that fraction. Kind of like numerically, if you have 2 times 3 over 5 times 7, you could think of this as 2/5 times 3/7. Okay, so that same idea where we're kind of group things where we want to so that it's strategic.
1 over cosh is
1 over
sech.
cosh is sech, sinh over cosh is tanch. So let's try this one. So same idea here. We're going to write this as 1 divided by sinh derivative. I'll let you try first. Try that quotient rule. I know quotient rule can feel a little rusty. There's all sorts of different acronyms for the quotient rule, or maybe it's not an acronym. All sorts of different methods to memorize it. Whatever it takes, make sure you have something. Low D high minus high D low over low squared. There's other variations of that. Bless you. And some of these, as you get faster, you don't have to write, sinh times 0 if you can sort of see it quickly. But if you're a little rusty on the quotient rule, it does not hurt to just write it all out. I ain't going to remember to take roll today.
Just remember, I'm not here.
Tanner's gone. Absent-minded.
You're looking quite worried there.
Blur,
Switched glasses when
Declan,
I was little.
Absent?
absent. Seth. Seth is absent. Let's see. Kyle is not absent. Christian is not absent. Race is not absent. Hayden is not absent.
Yeah.
Eric is not absent.
That is the
Lincoln is not
Except,
absent. Perry.
oh, did you spell that?
Perry is not absent. Robert. is not
But that
absent.
is the,
Matthew Hernandez.
okay, probably. Right.
Kirill.
That's fine. I just
Bryce.
don't understand your writing, it's fine.
Julian. And then McFarland. Matt McFarland, not absent. I think the other Matt's missed last couple days. Because he normally is here. Gerardo is here. CJ. Zach. Dustin. Emilio. Oh, yeah, you're on that side. Connor. And Siraj. Tim. Tanner. And Edgar. All right, so we stumble through that quotient roll, okay?
Yeah, keeping that -1 there makes it easily.
A little easier to see how you
Yeah.
can split it apart.
Yeah.
So let's do the same thing here. So low D high is 0 minus high D low. Yeah, so if we want to keep that 1 out in front, that might make it easier to see how it comes out in the end. Low D high minus high D low over low squared. And if we want to be clever, because we know where we're going, we could say, oh, let's just write that as sinh times sinh. And then we can strategically group things. So 1 over sinh is cosec. And cosh over sinh is cotang. So that's how we can find our derivatives, knowing just our basic 2. Well, let's go ahead and take a 10-minute break.
Yeah.
Take 10. Take 10.
Hang 10, I take 10.
Hang 10, take 10. Don't smoke 10. Long day.
Wait, 5 hours of walking or?
5 hours of skiing to get in, yeah. With a big backpack. Oh, should be fun. You all will be doing math.
Well,
Hopefully. Some math. Some math. Okay, let's take a look at a couple more derivatives here where we kind of wind in some product rule, chain rule, all that stuff. So go ahead and give that first one a shot, where we are taking the square root of cotang of 3x. Probably the first thing that might be helpful is to write your radical as a half power. That's probably a little helpful. Maybe not necessary, but can be helpful.
Yeah.
yeah, because you do
And you saw the 3x inside, so then you change the derivative.
Oh, yeah.
You take that derivative, or you take the derivative.
Chain rule coming back? Feel like you're being waxed by a chain. Good? Let's see, pull one carefully. Oh yeah, yeah. Looking good. Oh, the coefficient has print. But yeah, you
It is negative.
did the half down into the denominator, so that's all.
Is it ln of
2 or 3?
For some reason, my brain always forgets derivatives.
The 3?
Brain forgets everything important and remembers random YouTube shorts.
All right, so let's go through this. So the first part is the power rule part of it because we have a power. The power is the predominant operation. It's the first thing happening on the outside. So we always sort of start outside. So f prime, starting on the outside, bring the power down. When we bring the power down, we don't change the base. The base stays the same. So the power comes down, we leave the base alone, and then we subtract 1 from the exponent. So that's the power rule part. Down, same, subtract 1. And now we have to multiply by the derivative of the base. So that's the chain rule part of it. So now we want to multiply by the derivative of the base. So if you think to cotangent, derivative of cotangent is minus cosecant squared. So we know we're going to have a cosec squared. And it's also going to be minus because this is not one of the primary 3. Sinh, cosh, and tanh all have positive derivatives. If it's not sinh, cosh, or tanh, it'll be a negative derivative. So we're going to have negative cosec squared of x, 3x. And then chain rule again, keep on going, drill even further in and multiply by 3. And if we simplify this whole thing, we'll end up with negative 3 times cosec squared of 3x, all divided by 2 times the square root of cotang of 3x. Okay. Some good review with the chain rule and all its variations. All right, try this one. Natural log of sec 2x. chain rule.
You got the math next. Yeah, we just couldn't read. I couldn't tell.
No, but it's not correct.
Have a good day.
Negative such.
Oh, that's right, because secant is secant tan.
So when we differentiate a log, no matter what, the first thing we do is 1 over the inside. That's first step with the derivative of a natural log, 1 over the inside.
Yeah.
So we're going to do 1 over sec of 2x. And what could that be simplified to in the next step? 1 over sec.
Oh, sine. No, cosine.
Cosh.
Cosh.
Yep, cosh. So 1 over sec, that could be reduced to sec of 2x in a minute. So 1 over the inside multiplied by the derivative of the inside. So in my mind, I'm thinking, okay, well, secant, the derivative of secant is secant tangent, so it's going to have that flavor to it. But sinh, cosh, tanh, those are all positive derivatives, and if it's not a sinh, a cosh, or a tanh, it's going to be a negative derivative. So sec will have a negative derivative. So negative, and then we said sec tanh. And then we have to multiply by 2 as well. Now, we're not going to be able to simplify that 1 over sec to cosh because we don't need to, because those are canceling, right?
Oh, wait, over such 2x.
And so this is all going to reduce to negative 2 tanh of 2x. All right, so a good opportunity to review some basic Calc 1 stuff. All right, here's a product rule. I'll do the first one because it's easier. I'll let you all do the second one.
So generous.
So generous. The product rule here. So whatever your method of memorizing the product rule, I always do it as first derivative second plus derivative first times second. Now you can do first derivative second plus second derivative first, but there is a reason that I do it this way. There is a reason I go first times derivative second, and then derivative first times second, because when you get into calculus 3 and you have a product called the cross product, matrix multiplication is not commutative. And so it's really important when you take the derivative of a cross product that you do first derivative second plus derivative first second. If you switch the second to, it won't work. So it's a good habit to get into to start doing it now. So first derivative second, so we have a tangent. Derivative of tangent is like the derivative of tangent. Derivative of tangent is secant squared, so this is going to be a sec squared, and should it be positive or negative?
Negative.
Positive, because sinh, cosh, and tanh are our primary 3. Sinh, cosh, tanh should all be positive. Yeah, very easy to get. So first derivative second plus derivative of first times second. So we have that. And not a lot of simplification here. We're just going to write it like that. So there is our derivative. All right, you all try this one with a product rule and a chain rule or 2 or 3.
I hope I'm not doing this right. This is a mess.
So on the exam, there'll be a couple derivatives, couple integrals. You can look at the prior exams. Nothing totally crazy, but doing enough practice is helpful. You don't want to lose points in 7.3 because it's really Calc 1 with a twist. Calc 1 with some H's.
I hope I didn't do that right. That's gross.
The hard part is probably this first step where we have to do first times derivative of second. So if you need to, kind of separate it and think about the derivative of second. So first function, derivative of second. There's a lot of folks that really like to put that 2 up in parentheses like that, because it's a little less likely that you get jammed up with the angle and the exponent.
3x.
So 3x. So this 2 is going to come down and make the exponent 1. So we have that. That's the power rule part of it. Power comes down, the base stays the same, angle stays the same, and then we multiply by the derivative of the base. So when it's in parentheses, it's a little more obvious. The 2 comes down, it becomes a 1, then you differentiate the base. So just make sure that you get all the pieces here. The derivative of the base is going to be sinh of 3x times 3. So there's the first part. So first derivative second plus the derivative of the first, which is just 2x, multiplied by the second function, which is cos squared of 3x. And I don't see a ton of simplification there.
2 and 3. That's it.
That's about it, right? So 6 to the front, 6x squared, cos and sinh multiplied together. If you wanted to, you could probably try to find a double angle identity type of thing, but we don't need to.
Plus the.
And then plus that stuff over here. Perfect. All right, derivatives. Let's now do some integration. So, okay, the only technique that you really have so far with integration is u sub. And it's not obvious. Like typically when you've seen integration where we've used u sub, you're letting u be the exponent or the angle or what's in the square root. Not as obvious here. So we have to be a little bit more, we have to put on our detective hat and think a little more carefully. What we would like, the general principle is whatever we choose for u, its derivative is present, or a multiple of its derivative is present. So when we look here, the first thing I'm seeing is that this is, I could think of that as sec squared times tanh. So I could let u be sec squared, I could let u be tanh. You could also let u just be sec. That's also a possibility. So there's a lot of things that could happen. Now, the simplest, I think, is probably if we think about letting u be tanh, we know its derivative is positive because it's one of the primary three, sinh, tanh, cosh, sinh, cosh, tanh. And when we look at its derivative is sec squared. So this is perfect, actually. Right? So that's just going to be a u du. That tanh is going to be our u. Laser pointer. Let's go orange. So u, and everybody see that it's just going to be u to u? So the tangent is becoming the u, and then sec squared of x dx is becoming the du. So this is just going to become u squared over 2 plus c. So we'll end up with 1/2 tangent squared of x plus c. Must have made that bigger by accident. Does that look right to everybody? All of a sudden the ink just feels like it's bigger. Okay, how about 39? You all try 39. Anyone done with it yet?
That's what it feels like. You have 5 seconds per problem.
This thing should only take 5 seconds.
I agree. Not for me.
I think I'm gonna. Wasn't horribly wrong, it's just,
Yeah.
logical.
Do you see what form it's in? Log form?
Oh.
Log form? As long as the denominator's derivative is identically the numerator, you can write down the answer immediately. The answer will be natural log of the absolute value of the denominator. And we're done. So if it's in log form, you can cut to the chase. Do we need those absolute values in this case?
No.
No. Cosh is the hanging cable. Cosh is always positive, so we don't need. Would I take off if you left them there? No. But you don't need them.
If it were 2 minus cosh, or no, cosh minus 2 or something like that, you would, right? Because it can go to,
Yes, exactly.
it goes
Yep.
slightly below.
Right. Yeah, if we had some sort of shift down of cosh, then we'd have to leave them. Yep. Correct. All right. Go for it. Go for it. We're seeing what to choose for you. Yeah, so if you choose something with the square in it, then you're going to have to pull that 2 down, and you're going to end up with a gnarly chain rule thing. So usually you're only going to want to let it be a single function, like cotang or cosec, usually. Because if you let it be a squared function, usually it's going to get really gnarly.
Derivative of cot is saturated, so. I think I might be doing something.
Struggle seems to be real. When you think of cotangent, the derivative of cotangent is minus cosecant squared. So think about that. So if you let u be cotangent, its derivative is a square. So that's kind of a hint. If you think about Don't think about eliminating that 2 in your mind for a second there. If you let u be cotangent in this case.
That's where I was at. Second guess myself.
Oh, it's wrong?
Yeah, so this is not the right derivative. Because if you are gonna let u be something squared, that 2 is gonna come down, then it becomes a 1, then you also have to take that derivative, so you're gonna end up with something that's really complicated. It's very rare that you wanna let u be a trig function squared, very rare. Does everybody see if you were to let u be, say, cotangent squared, here's what the gnarly derivative is going to look like. You're going to get 2 cotangent to the 1 multiplied by the derivative of cotangent, which is minus cosec squared of x dx. And that may look like it's a good match, kind of, but notice that you'd be letting this be u, and cosec squared dx, you have this extra cotangent that has nowhere to go. So you don't want to do that. So usually we want to let u be just a single trig function in these types of things. So what we're going to do is this. If we let u just be cotangent, then you can think about this as being u squared. Cotangent squared would be u squared. All right, and the derivative here is minus cosec squared of x dx. So that's going to be the best match. So that will end up giving us integral of u squared times negative du. We'll put the negative on the outside. So that's what it all simplifies down to, integral of u squared. So that's going to be negative u cubed over 3 plus c. Then we'll back substitute, make that negative 1/3 hyperbolic cotangent, aka cotangent cubed, plus c. Does that make sense to everyone? Okay, so just like with the trig functions, the circular trig functions, sine squared and cosine squared can't be integrated directly. You had to power reduce them. Same thing here, we're going to have to power reduce. So if we come back, we want to power reduce sinh squared. It's going to look a lot like the power reduction for sine squared. It's just that the numerator is flipped. And same for cos squared, the numerator is flipped. Doesn't really matter with cos though, because it's a plus, so it doesn't really matter. So sinh squared, power reduction, will be cos of 2x minus 1 divided by 2. So, wrong slide. So this is going to be equal to the integral of cos 2x minus 1 divided by 2. So just like we did with the circular functions, we can pull out the 2 in the denominator, and then we can just integrate term by term. We can, in fact, use the reverse chain rule, just like we've done. So that integral, that first term's integral, the integral of cos is sinh. So we're going to have sinh of 2x. Angle stays the same, but then we have to divide by 2. So that's RCR, reverse chain rule. Divide by the derivative of the angle. And then the integral of 1 is just x plus plus c. We can simplify that a little bit. So that'll be equal to 1/2, let's see, let's make that a fourth, times sinh 2x minus 1/2 x plus c. Not too bad. A little reverse chain rule. All right, any questions on any of those? Any of those steps?
How do you identify that you're going to use a reverse chain rule?
Whenever there is a linear substitution.
Okay.
So you could use substitution there. Classic substitution is to let u be an angle. So if that angle or the exponent or what's inside the square root is linear, that's what sort of clues us in that you could go substitution, but you could just cut to the chase and divide by that derivative. So whenever you see a function that has a linear function inside of it, that's when we're going to go RCR. Let's go last slide in 7. So we've got this kiln thing. We want to find the volume of the inside. It's the front is an inverted catenary.
Couldn't have just made it.
Right? Why not?
Well, is catenary is the optimal arch, like the optimal arch of the catenary, same thing as a hanging chair.
Think of St. Louis arch. That thing is an upside down catenary because it is the strongest type of arch under its own weight.
Every historical dome.
Yeah, so if you start looking at all those doorways, you could make an elliptic doorway, but the strongest arch is going to be a catenary. Can hold its own weight. Okay, so the front of it is this upside down catenary, and of course we just multiply by 6 in the end to get the volume. The important part is trying to find the area of that face. So the area of the face here, we are going to have to integrate this function from this left endpoint to the right endpoint, but we have a little bit of a snag here. What are those endpoints? Let's see. So if we set this function equal to 0, we don't know, like the circular functions are nice because we have a bunch of points that we can find values of exactly. Hyperbolics, we only know cosh of 0 is 1 and sinh of 0 is 0. Those are the only two special points. The rest of them are a mess. So here we're going to have cosh of x is equal to 3.
This is where we get out Desmos.
This is where we get out Desmos, that's right.
Or can't we use the fact that like we know area under the curve or something like that for?
I don't think there's going to be any shortcut that you're going to find here. So inverse cosh of 3, that says the hyperbolic, x is the hyperbolic angle. So it's the hyperbolic angle with a cosh of 3. So the cosh value is 3. There's going to be 2 of those x values, right? So we could, I think symmetry is going to be a good way to go here. And let me just kind of say what I said there with a little picture. So if we think about our catenary as just hanging like that, if we wanted cosh of 3, right, there's 3 right there. That's not to scale. But, right, if we set the catenary equal to 3, we're going to have 2 x values. We're going to have this one and this one. So we're finding those 2 x values. Okay, but let's just leave it in exact form. Let's not approximate. So if we wanted to set up this integral, we are going to say that the area here, we're going to use symmetry. So 2 times the integral from 0 to inverse cosh of 3. And then our integrand, oh my gosh, is this function. So So we're going to do that. And then we can integrate term by term. So we're going to have 2 multiplied by integral of 3, of course, is just 3x. Integral of cosh is sinh. Don't need any chain rule or reverse chain rule there, so that's it. And then limits of integration. So if we plug and chug, we're going to end up with, I'm just going to make that 6x. Do you agree that if we plug in 0, we get 0? 3 times 0, of course, is 0. And sinh of 0, remember, sinh looks a lot like tangent. It looks a lot like x cubed. It goes right through the origin. So sinh of 0 is 0. So this is not going to contribute anything down there. So we're going to end up with 6 times inverse cosh of 3 minus 2 times sinh of, we're plugging that in, right? So for the x, we're plugging in the cosh inverse of 3. So that would be our exact answer. And if we want an approximation, we'll just type that into Desmos. All that stuff lives in Desmos. Like any math, Desmos has everything. Well, not everything.
4.919? Let's see.
Let's see. So we're going to get 6 cosh inverse 3 minus 2 sinh of
Aha! 4.919.
And times 6 for the volume.
So when we do cosh inverse, is it clear why we're getting just the 1 value and not the 2 values?
No.
So how about when you type, let me just copy this first, then I'll talk. So, all right. So when we're dealing with trig functions, let's suppose we have something like this equation. Sine of x is equal to 1/2. So you might say, oh, that means that x is equal to the inverse sine of 1/2. Is that true? That's only going to give us one solution. Maybe I'll call that x sub 0. That's going to give us one solution. Most trig equations, circular trig equations, have infinite solutions. It's not dissimilar from the hyperbolics. So up here we have a hyperbolic equal to a constant. This hyperbolic equal to a constant is going to have 2 solutions. It's not going to have infinite solutions, but it's going to have more than one. We can see the 2 solutions right there. And we want the inverses to be functions. So what we choose is a primary value for the inverse. So when we're looking down here, if we were to look at this setup here, this unit circle would tell us that there's an infinite number of solutions, a family in quadrant 1, a family in quadrant 3, and if we wanted all solutions, we would say x is pi over 6 plus 2 pi k, or 5 pi over 6 plus 2 pi k. Right, that's all solutions. But when you type that into your calculator, what does it give you? Just gives you the 1 in quadrant 1. It gives you pi over 6. It gives you the first one. It gives you the primary one. And so that's the idea, is that if you want your inverses to be functions, you have to restrict and say we're gonna collectively agree that the primary inverse for sine is going to be that one. So we say the inverse sine lives on the right side of the unit circle. It's always an angle between negative pi over 2 and pi over 2. Right? Whereas if we graphed, if we were to look at a graph of sine, obviously there's, so we've got that kind of thing. Oh, that's funny. So it's going to, are you going to erase again? No, good. So if we went to 1/2, here are all these solutions where sine is equal to 1/2. What we're choosing is to say that our primary cycle is going to be, this is going to continue that way, and it's going to meet again there. But what we're saying is that our primary cycle is going to be right here, in this interval right there, -π/2 to π/2, the right side of the unit circle. So we're choosing that. We've agreed that we're going to say that's the inverse value of choice. So same idea with this hyperbolic here. The inverse value of choice is going to be the one that's over here on the right, positive x value. Certainly it's symmetric though, right? This is 1.76. That's going to be that x value. That one's going to be negative 1.76. That makes sense? Now, inverse sinh is a little different because inverse sinh is 1-to-1. So there is only one possible value for the inverse of any x value if you looked at inverse sinh, because it's a 1-to-1 function. It passes the vertical and horizontal line test. So, all right, so that's why we get just one value. Now the final answer of the question said, what's the volume? So volume, I think the depth of it was 6. So it would be 6 multiplied by this number up here, rounded to whatever they wanted us to round to. So we would get whatever. Type that in. So 25-ish, what is it?
29.5.
29.5.
A bit less than 30, a bit less than 5 times 6.
Snug less than 30. Yep, right, yeah, makes sense. All right, so there's chapter 7. Now we are officially through with the first unit. And what I want to do now is drill you with some of the things that tend to take extra practice to master. So that is finding work draining vessels. So I'm going to give you, we're going to start our review now so that you will be so ready for the first exam. You're going to make the grading so easy. It's going to be like, wow.
You'll be saying wow, right?
I'll be saying wow for the wrong reason.
Administering the test from his ear.
Okay, so let's go to, I think I'll just add these slides at the end of this, and since this is where we're at, let's just add slides in here. Okay, so the first one I want you to work on is this. So we had 3 different shapes for our tanks. We had cylinders, cones, and troughs. Those are the 3 types of shapes that you will see. And so let's give you the easiest one first. That's the cylinder. So let's suppose that we have a cylinder that is going to be filled with, we'll choose water because water is the easiest thing to deal with.
Are you
So-
sure you don't want to do acid to make it more difficult for us?
I'll wait till the exam.
Oh, nice.
Then we'll do acid. I didn't say that. Okay, so there is our tank. We're going to imagine that it's filled with water. So remember that the density of water is what?
1,000
A
kilograms.
1,000 kilograms per meter cubed. So there it is, and we're just going to empty it. Let's up the ante a tiny bit. Let's suppose we're going to empty it out of a pipe that comes up an extra meter. So we're going to empty it out there where this distance right here is 1 meter. Up the ante a tiny bit. Just a skosh. All right, so find the work.
Yeah. Cross section.
Let me know if you're stuck on something. I can come and nudge you.
13 minus 1 then?
Does the little spout add change the integration limits, or does it change the y is called and y minus 13? Or 13 minus y?
It won't change the integration limits. The integration limits are always the physical location of the
Okay, so
water.
you just change 13 minus y.
Just changes the distance that a representative cross-section travels.
Minus 12 squared is just 13.
It's 12 squared over 2.
Because we take on the time.
Well, you're working with the.
Perfect. Yep, that's all right. So volume, by volume, remember, we're talking about volume of a slice.
So you have your height too.
Height is dy.
dy.
Yep.
So,
So it's not the volume of the whole tank.
yeah.
The volume of just that little slice.
He's 9.8, right?
Yeah.
Acceleration.
Yep, 9.8 density, and then distance that that slice travels or that cross section travels. Close, if we're gonna go 1 meter above and come out that pipe, then
13.
that's 13 minus y. Right. Let's see. So, okay, that. So this is backwards because if this whole distance is 13. Right, exactly. Yeah, so we're taking that away. So the distance up on top is 13 versus half. Okay, so now if we, you already passed for 6. So if we look at this cross section right there, just when we talk about volume, we really want to look at the slab, slice. So the volume of that is the area times dy. So what is the area of that is? Area of this, like circle,
Okay, that one I wrote.
r squared. And what's the r?
Just that bad.
Great, yeah, exactly. Exactly.
Okay, one.
So let's go to here, pi r squared. So you good? So that's what's that number? So that number is our, because we're going not right out the top, we're going a meter above, so this layer of water has to travel 13 minutes long. Leaving a meter above the tank. Here's coming. Wait, am I supposed to be able to read this?
7.
Okay, I can read it now, And that, those limits right, yeah, that's all.
On exams, do you want us to box final answers?
Ideally, yes. As long as I can see them clearly. That's a lot of work.
Oh,
What are the units?
yeah, I did. So yeah, that's 5 million times Q.
God, yeah.
There goes.
Ah, there it
Let's see, so that. Yeah, you did good. Let's check.
Right, because you just care about the water. The water.
Zero's coming.
But you need that water total.
then.
Nope. Nope. So this is the easiest case because all those cross sections are gonna have the same area. They're all discs. There's not like a tilted side where we have to build a function, so it can factor right out to the front.
If we do our work on the test, if we do our test in white colored pencil, and you would just automatically get 100% because you can't read it, because you can't prove it out wrong.
Well, if you can't read our handwriting, you just prove it.
I think the burden of
Wait.
put onto the person who wants
Did I just hear what I think I heard?
So white colored pencil to do the test.
Yeah.
Therefore, you can't read our handwriting.
Continuing
I
forward,
think it's
the work, please don't use invisible ink. So the acronym is going to be ADD volume.
Or make it easier for you, yellow highlighter.
Oh, God.
The easiest thing is to just do what you're supposed to do, right?
what is supposed to defined as, please?
Correct work. Do math correctly.
I did do the math.
Don't
correctly.
invent math.
No.
Art classes are meant to invent things. In math, you're supposed to not invent new math. Not yet.
That comes later.
That comes later. Okay, so we have our tank. ADD is acceleration density depth, or acceleration density distance traveled. You can think of it in either way. So acceleration, 9.8. The density of water is 1,000. The distance traveled by a representative slice, it has to go all the way out up here. So this distance is 13 minus y if this distance is y. Because the full distance is 13. If you take away y, what's left is 13 minus y. And then we have to deal with the area next. So 13 minus y. And this will go 0 to 12. The limits always reflect the physical location of the water.
So it's not 13?
Nope, this is 13 here because the distance that slice travels is 13 minus y, but we only have slices of water from 0 to 12, right? From that 12 to 13, there's no water that travels. So the limits always are the physical location of the water. And now volume, by volume, what we mean is volume of this slice of water right here. So if we add thickness to that cross section, that is now a tiny volume of water. And again, because every cross section is a disk of radius 3, the area piece is always 9 pi. Pi r squared, so pi 3 squared, so 9 pi. So that's going to be 9 pi. That's the area, and then the thickness is dy. So that is now, this is the volume of a slice of water. And again, the cylinder is the easiest one. Everything comes out except for the 12 minus y, 13 minus y. So we get 9,800 multiplied by 9 pi. And then we can probably integrate this right away. Integral of 13 is 13y. Integral of y is y squared over 2. Those go from 0 up to 12. 0 doesn't do anything, so we just have to plug in the 12, and I'll just write etc. So that's the part that's important, getting up to there. Use your calculator for the rest.
7.4 times 10 to the 6 pi.
Say that again?
7.4 times 10 to the 6 pi joules.
Great. All right, so now let's try the next hardest one is the cone. That's the next most difficult one. So let's add a new page, and let's do a cone.
In your answer. Gotcha.
So let's suppose that this cone is, let's call that 9 meters high. Let's say the radius there is 2. And let's suppose, I think that's all I need to give you. Height is 9, radius is 2. So same question.
Water rate?
Filled with water.
Water on the surface of Earth.
Water on the surface of Earth.
water on the surface of Earth. And it's just going up to,
Right at the top. We'll just do this one right at the top.
somewhat nicer. Actually,
Plus 0.
it's not 12.
No, it's not. I'm thinking of that.
Close, which it was.
What is the radius bound?
I,
For areas, not concepts. Areas. That's gross. No, it's two
It's two
nights.
nights.
It's 2 nights.
Two nights.
It's backwards.
Yeah, okay. Yeah, I was gonna
And
say.
for slope in terms of y, it's run over y.
Yeah,
So
exactly.
it's 2 over.
So it was. Be snarky like these things.
Is there any questions getting to the ADD part and the limits? ADD part and limits? Let me make one general comment. So we're thinking about a pump. This water is being pumped out of the tank. So the pump is what's doing the work. If we were to just open the drain at the bottom and let gravity do the work would be the same. It's just that the work would be being done by gravity instead of by a pump. We're going to follow that? So if we were going to drain it out the bottom, what would be the distance traveled by the cross-section at y? The top cross-section would be 9, but what about the cross-section at y? How far would that travel?
0.
The cross-section at the bottom would travel 0.
9 minus 1.
0, y minus 1.
I don't think I've heard it yet.
0 minus 1.
How far, so there's your y. How far above the bottom is it?
Why?
Y.
Just why? Okay.
So if we were going to drain it out the bottom, this whole piece right here would just be a y.
Because y gets bigger.
And so we're still going 0 to 12, so we're still going to have all slices. So the slice up here, or 0 to 9, so the slice up here is going to travel 9, the slice in the middle is going to travel 4.5, the slice here is going to travel 1. So all those slices will still travel, different distances. Now here's another question. If we have so do you think the work done by gravity and the work done by the pump would be the same in the case of a cone? So in the case of a cone, the work will not be the same. If we have a cylinder, the work done by the pump at the top and the work done by gravity will be identical. So technically on this one, if this was not emptied, if this was just emptied out the top, if it was emptied out the top, the distance would be 12 minus y instead of 13y minus y. If you just replace that with y instead of 12 minus y, you get the exact same answer. Now with the cone, it's going to take the pump do you think the pump's going to be less work or the gravity less work?
The gravity.
Gravity is going to be less work because why?
Because it's not. Or the pump is fighting gravity.
Well, because at the top you're moving more water.
So what's doing less work?
The pump.
The pump is doing less work than gravity because this chunk of water up here is going to travel less for the pump.
More water.
Now it's easy to think gravity's not really doing anything, but gravity would have to pull this whole bigger chunk all the way down to the bottom. So the bigger cross sections are going to travel further with gravity than with the pump. So if you calculate this whole thing with the 9 minus y, that's the work done by the pump. If you replace the 9 minus y with y, you'll see, if you go through the math, you'll end up getting less work for gravity, less work for the pump because the bigger cross sections are closer to the pump. The bigger cross sections are further from where gravity's pulling them to.
Would most pumps have something going to the bottom and then have gravity do most of the work?
I mean, that's an ideal situation like with dams and things. If you can somehow get gravity to do most of the work, that's so they're doing that stuff, right now with those dams where when power costs less, like in the middle of the night or whatever, they pump it to a higher reservoir and then let gravity pull it during the day when things cost more and they can let gravity do it for free kind of thing. So there's that stuff. Okay, so then what about now we have to get our volume here. And again, volume is not volume of the vessel, it's volume of that slice of water. Now, unlike the cylinder where all slices have the same volume, all slices have different volumes. So we need to come up with an equation for the radius here. And a simple way to do it is to look at this line right there. And we can come up with the equation of this line really easily. This line goes through the origin, so its equation is y equals mx, slope times x. So we're going to go up 9 and over 2. So that equation is y equals 9/2 x. Up 9 over 2, we have a right.
9/2 y?
Say again?
9/2 y?
9/2 x.
Oh, sorry, you converted it.
We haven't solved for x yet. We are going to solve for x. So the equation of this line, y equals mx plus b, b is 0. We go up 9 over 2, that's the slope. And now we want to isolate x, so x will be equal to 2/9 times y. And so that is our radius function. So that radius is the radius at a height of y. When we're at 0, the radius is 0. When we're all the way up here at 9, plug in 9, they cancel, we get a radius of 2. So what goes in over here will be pi times the radius squared. So pi times 2/9 y squared times dy. So here is our volume. And again, that's the volume of the slice.
Oh, I added the pi in again.
Does that all make
I didn't actually finish the 20.
some sense? Let's factor out the constants. We get our 9,800. And then all that constant stuff in there, we can pull out a 4 over 81 times pi. So make that 4 pi over 81. And let's see what we have left. Integrate from 0 to 9. So there's a y squared that gets distributed, so we have 9y squared minus y cubed times dy. Let's integrate that. So we're going to get 3y cubed minus y to the 4th over 4. And that will go 0 to 9.
So we are using the 9 minus y equation
Oh,
for
yeah.
the distance traveled, or just the y?
9 minus y if we're doing the pump. So empty, I didn't,
Because
out
the
top.
It's not the same.
So we're going to empty it out the top. If we empty it out the top, out the top.
Because with a cone, it's not the same. It's not symmetrical.
Yeah, with a cylinder, you could cheat a little, and instead of the 12 minus y, you could put just y and get the same answer.
Because when you end up doing it, it's basically just y squared minus y squared over 2, right? If you have a cone.
Yes.
cylinder. Yeah.
So you get y squared over 2 instead of that two-term thing, so you have a little less work. And then we'll plug in the 9. Plugging in the 0 doesn't contribute, so did anyone get all the way to the end?
264,660 or 600. Sorry.
Wait, start over?
What, sorry, 264,600
Times pi
times 5.
times
Joules.
joules. Okay.
I can't.
You scroll back up.
Yes. Yeah, so is there any, so this would be, let me just put in parentheses here, this would be if gravity. Out bottom. So if we were going to do it out the bottom, so you can calculate that just to see what the magnitude of difference would be. So if gravity out the bottom, the only thing that's different is this. Those are still the same. It's just that the distance traveled changes per slice.
But wouldn't we also technically flip, it would be from 9 to 0 then at that point, and you'd make everything negative?
I mean, if you wanted to, you could invert everything like that. You could go 0 to 9 though, and it'll be fine because you still have all those slices being pumped out the bottom.
Sure.
Yeah, so you can think of it. Same slices.
Same magnitude.
Same magnitudes.
You start at the bottom.
All right, let's stop there. See you on Tuesday. Have a great weekend. Study up. We'll review all day Tuesday and
You can pull out all these constants.
yes. And so that's what
That's
we're
where this is
doing.
right here. Yeah.
That's right. So this
So basically, you're
That.
doing two
That.
nines squared, and then, so yeah, 2 nines squared is 480, 480
first, yep.
480 first, and then bring over the pi. So
Bring
just
over the
pull it out
pi.
front, and then
Mhm.
take that,
We're going to take
and the
that and the y squared and distribute that y squared to
in
each
here,
of those.
take
Take the integral.
Take the integral, and then plug it in.
Plug in our limits. Yep. That's right. That's it.
Gotta remember doing rise over right here,
Right?
and
Yes.
then finding x.
Yeah, once you see it, it
Yeah.
becomes really like, oh yeah, how come I didn't see that
Of
earlier?
9 over 2.
Of 9 over 2.
So y equals 9 over 2x, and
Yep.
then convert it to x.
Yep.
Yep.
That's right. That's right. And once you see it, it's like, oh
The
yeah.
last one's the hardest.
Yeah, the trough is the hardest. Trough is the hardest. Definitely.
Just bring your stuff in.
Trough. The trough is the hardest. Connor, question?
Something's been bothering me
Yeah.
about the shell method. So,
Ah, I can't wait to hear this.
so I remember, or if we just like graph like that, and we rotated it about the y-axis.
And what is our region? So we have to have a closed region. Are we rotating this? Are we rotating that?
Oh, this.
Okay.
Like this right.
Okay, gotcha. Okay, so that's going around the y-axis.
But we would. So that would just be a circle and then or a wash or not a wash.
So if you're going to make a shell, you would have to draw your element parallel to the axis of rotation. So this if you're gonna go around Y, you would have to draw your element that way. So,
That's why.
you see
that's
it?
why it threw me off because I was like, why do we differentiate this with respect to Y, but with the shell when we rotate it? We differentiate it.
So the whole key is that if we want to create a cylinder or a shell, we have to be parallel. So these have to be parallel. The radius will then be perpendicular. When you find the, see you, have a great weekend.
You too.
So when the radius of it will be horizontal, the height of it will be vertical, so we'll have to, align it so that they all match.
That makes sense now.
Once
Thank
you see it, that it creates a cylinder this way, if you rotate that way, it's going to create a disc or a washer. If it's touching, it'll create a disc. If there's a gap, it'll create a washer. Yeah, so here, if we're rotating around Y, you could use disc method if the functions were nice. But if you're asked to use shells, then we'd have to do it that way.
Okay, that makes sense. I get it now.
Cool!
Thank you.
Uh-oh, what happened out there? Yeah. Winter?
Yeah.
Winter.